Okay, so while we wait for others to join, let me just recap what we were discussing in the last class. So we're looking at this problem again, which is vertex cover. Okay, so we already saw 1-2 approximation for the problem. So how did that 2 approximation work? Is that we took a maximal set of disjoint edges. So those edges do not share any endpoints. And then we picked both the endpoints of those edges in our vertex cover. Then we argued that this gives the 2 approximation. So the solution we'll get is at most twice the optimal solution. But it is slightly unnatural because why would you go to this disjoint set of edges? So the most natural, the first algorithm which comes from first greedy algorithm, because most of the approximation algorithms they follow this greedy approach, right? So what we would like to do is that we should pick a vertex which is covering as many edges as possible, right? And then we keep on repeating this procedure, and finally we stop when we have covered all the edges, right? It's probably the first thing which will come to your mind when you are dealing vertex cover or any other problem. Okay, but unfortunately, certain cases this gives a slightly worse approximation, maybe even worse. Okay, and that's what we are going to see today. Okay, so uh, so we started initially our vertex cover did not have any vertex, so C is set to empty, and E prime is the set of edges we have covered, we have not covered so far. Okay, so initially our vertex cover is empty, E prime consists of all the edges, and then we pick a vertex with maximum degree and add it to our vertex cover. And once you add it to your vertex cover, then we'll remove V and all the incident edges from this set. Okay. Now, because V is there in your vertex cover, that means you have covered all the edges which are incident with V. So all the edges whose one endpoint is V. So you'll have to remove all these edges and also remove the vertex from this set E prime. Okay. And finally, we return the resulting vertex cover. Okay, so very standard greedy algorithm is that every step you pick a vertex which covers as many edges as possible. So we pick the vertex V with maximum degree. Okay, and we were looking at this example, which is a bad example for this particular strategy. Is that let's say you have some vertices at the top. So this is an example of a bipartite graph, right? Because all the edges are going from bottom to top. There is no edge between a top vertex to another top vertex or a bottom vertex to another bottom vertex. So all edges are going from top to bottom. Okay. And let's say we have this k factorial. K factorial, I hope you all of you know, it's the product of 1 to k. Okay. There are this k factorial vertices of degree k at the top. At the bottom, we have these particular vertices. So there are k factorial divided by k vertices of degree k. Okay. So degree k means it is connecting to k vertices at the top, every vertex here. And all these vertices are connected to different subset of top vertices. Okay. So if there are k factorial vertices at the top, you need to have k factorial divided by k vertices at the bottom. Each of these bottom vertices is going to connect itself to k vertices at the top. Okay. And similarly, you can have another set of vertices which has degree k minus 1, degree k minus 2, and degree 1. Okay. So again, the same thing, every vertex is connecting itself to a different subset of k minus or a disjoint subset of k minus 1 vertices at the top. Okay, so you need to have k factorial divided by k minus 1 vertices to cover all the vertices at the top. Okay. Similarly, you can have k factorial divided by k minus 2 vertices of degree k minus 2 and so on up to k factorial vertices of degree 1. Okay, so this is the graph we are looking at, and we want to find the optimum vertex cover here. Okay, so because all the edges are going from top to bottom or bottom to top, one option is you pick all the vertices at the top, right? Then it is going to cover all the edges because every edge is incident with at least one vertex at the top. Okay, and so one natural vertex cover is that we pick all the k factorial vertices at the top, and that will give you k factorial size of that vertex curve. And it turns out that this is in fact the optimal vertex curve. Okay. Maybe you could also think of, let me pick some vertices from the top and some vertices from the bottom, but then you have to cover many different edges and you will have to pick a lot of vertices at the bottom. Okay. So now let's look at how, if we apply this algorithm to this particular graph, how does it look like? Okay. So what we are doing, we are picking a vertex B with maximum degree and adding it to our vertex cover, and then we have to remove this vertex and all of the incident edges from E prime. So what is the maximum degree here? It's K. Right? No vertex has degree K plus 1. Maximum degree is going to be K. Okay. Now, either you could pick a top vertex of degree k, so you could pick any vertex at the top, or you could pick the one among these k factorial divided by k vertices of degree k. Okay. So let's look at this bad example. Let's say our algorithm chooses to pick from the bottom. Okay. Because the only thing it is looking at is the degree. So it doesn't know which one to pick. And let's say it picks one from the bottom. And if it does so, then after that step, it will remove that vertex on all the incident edges from E prime. Okay. And let's say it has picked all the vertices at the bottom because all of them are of degree k. Then what happens is that every vertex at the top will lose at least one neighbor. Okay? Or in fact, it is losing exactly one neighbor. Right? Because all these vertices were connecting to disjoint subsets of the top, right? So there are these disjoint subsets of each of size k, and since we are removing all the vertices and the incident edges, so every vertex at the top is going to lose one neighbor, and therefore in the resulting graph, these vertices will have degree k minus 1, and all these vertices are removed from the graph. Now it turns out that the maximum degree is going to be k minus 1. So again, either you could pick from the top or you could pick for the bottom. Okay. Let's assume that again we pick from the bottom. Again, every top vertex is going to lose one neighbor. So the maximum degree here is going to be k minus 2, and at the bottom also it is k minus 2. And you keep on repeating this procedure until you reach this degree 1 phase. Okay. So if our algorithm is never choosing any vertex from the top, then it will pick vertices from the bottom. Okay. And then we just look at the resulting vertex cover where every vertex is picked from the bottom. Now all edges are covered and the total size is going to be this much. K factorial times 1 by k plus 1 by k minus 1 and so on to 1. And you can approximately write this as k factorial log k. Just integrate 1 by k with dk. Okay. That will give you this log k. Okay, this is called a harmonic series and the standard summation of, so all the inverses of these elements will be in arithmetic progression, right? So this is called a harmonic series and this summation is very standard, it's log k. Okay, so you have some strange summations, just integrate that particular function and you'll get the approximate sum of these things. Okay, so the optimal was k factorial, but here we are getting solution of k factorial log k. So it is a worst algorithm, log k worst algorithm. And now we want to prove some kind of guarantees, right? So, I mean, what is the size of the optimal vertex curve? Okay. So how are we going to compare it with the optimal vertex cover? That's what we want to decide. Right? We are given this particular algorithm. How do you even proceed to uh, first, what is your guess and what is going to be the approximation factor, and then we'll see how to prove it. Okay, so I have shown you a bad example. These kind of graphs, it's going to give a log k factor here. So what do you guess? In general, if your graph has n vertices and whatever the m edges, then what's the approximation factor? Yeah, any guesses? Okay, so let's see. So it turns out that it is a log n approximate vertex cover, right? So whatever vertex cover we are outputting by this algorithm, it will be at most log n times the optimum, okay, where n is the total number of vertices here. Okay, so for instance, here we got k factorial of k. This is not exactly log of n. I mean, it's smaller than that, but in general case, we will get at most log n times the optimal vertex curve. Okay. So why is it log n times the optimal vertex curve? Yeah. So the way we are going to argue is we are going to look at this particular algorithm and then we have to argue about the approximation factor. Right? So initially we started with this original graph, it had all the edges and then we steadily removed vertices and edges from this graph. Right? So at every step we are reducing the number of edges. Right? The question is how much can we reduce? Can we give some uh, guarantee that after these many iterations, the number of edges will reduce by this much? Okay, and that will kind of give you this guarantee that it is at most log n times the optimal or whatever. Okay, so yeah, how should we proceed to prove this approximation factor? Okay, yeah, let's see. So this is what we are doing is that initially we have to cover all the edges. Okay, so let's call this cardinality of G to be the number of edges in the graph. So this is our original graph and then we are picking a vertex of maximum degree, deleting it from that graph, deleting the incident edges with that from that graph. So you get a sequence of graphs. So G1 has possibly less number of edges than G0. G2 will have less number of edges than G1. Okay? So every time we are picking a maximum degree vertex in G0 and deleting all the incident edges and getting G1. Then we are picking the maximum degree vertex in G1 and deleting all the edges incident to it and get graph G2. And let's say we process this for Gn many steps. Okay, because we said that m is the number of vertices in the optimal vertex cover. Okay, so in every step we are adding one vertex to the vertex cover, so we'll get totally these many graphs G0, G1 up to Gn, right? So this is just formally stating what we are doing in health. Okay, and then what we are doing is that we pick a maximum degree vertex of Gi minus 1. Okay, so when initially I is 0, sorry, I is 1. So we pick a maximum degree vertex of G naught and call that degree, let's say D naught, and delete edges incident with them to get this new graph, Gi. Okay. So in each phase, how many vertices, how many edges are we deleting? It's the degree of this vertex, maximum degree of this vertex. So Di, right? This is in one step. We are deleting Di many vertices. And so totally, what is Di? It's the maximum degree vertex of G naught, right? So after m phases, the number of edges will be G naught minus summation Di. Okay. So G naught was this total number of edges in the graph, and then we are subtracting these many edges. Right? In each step, this is the maximum degree. So in each step, we are deleting maximum degree number of edges. Okay. So now we have got this equation that Gm equal to G naught minus this much. And then we try to prove a lower bound on this term. Okay. So what is the summation I equal to 1 to m di? Okay. Now, how do you prove it a lower bound in terms of the GIs? Right? Sorry, is there a question? Okay. So now we have to use some property of our graph to get some kind of lower bound on this summation DIs. Okay. Now we'll use the fact that our optimal vertex cover is having size m, right? So what we know that in any stage, okay, so whatever graphs we are considering, we always have this vertex cover, right? Because this vertex cover was in fact, sorry, yeah, okay. So what we know is that at any phases, this particular M size vertex cover was covering all the edges. So even after you delete some edges from this graph, this vertex cover is still going to cover them. Okay. And then what can you say about this? Because all these edges can still be covered by these M vertices, right? So there are these M vertices which are covering these Gi minus 1 edges. Okay, and then you can apply this pigeonhole principle that if there are m vertices which are covering Gi minus 1 edges, that means there is some vertex which is covering these many number of edges, Gi minus 1 divided by m. Okay, because if it was covering less than this number of edges, then the total number of edges covered would be less than Gi minus 1, and that would be a contradiction. Okay. So there is a vertex with degree at least this much, Gi minus 1 divided by n. Okay. So that's what we get, an upper bound or a lower bound on di. The di is at least Gi minus 1 by m, because we are always picking a maximum degree vertex, and we said that there is a vertex with degree at least this much. Okay. Now what can you say about this term? Summation I equal to 1 to m Gi minus 1 divided by m. Okay. This again can be lower bounded by summation I equal to 1 to m Gm by m, right? Because we are doing this for m many steps, and Gm has the fewest number of edges, because in each step we are deleting certain edges from the graph, and finally this is the final graph we are getting. Hopefully at zero number of edges. Okay? So we can also lower bound this term by replacing Gi minus 1 at every step by Gm. Okay. So we get summation I equal to 1 to m Gm divided by m. Okay. And this summation is just Gm, right? Because the same terms, these are independent of I, and I is varying from 1 to m. So it will be Gm by m multiplied by m. Okay. So it becomes Gm. Okay. So now we have got a good, what's the problem? Yeah. Okay. So this becomes GM. Okay. Uh, so now we substitute this fact into this equation fact. Okay. So we get that G naught minus GM, right? Because we lower bounded this thing is greater than equal to GM, right? Because we know that summation DI is greater than equal to GM. Okay? So since we have a minus thing here, so this thing will become greater than G naught minus GM will become greater than equal to GM. Okay. So that means that G naught is greater than equal to twice the number of edges in GM. So what are we saying? After m iterations of this algorithm, the number of edges has become half or possibly even more, right? So, and that will, this observation is very critical because in m iterations, we have deleted half of it. Okay? And finally, when do we stop? When there are zero number of edges. Okay. So how many iterations of this algorithm will require? It's m times log of the total number of edges in this graph, right? What is the total number of edges? Maximum is n choose 2, right? Even assuming that there are edges between every pair of vertices and it will become cardinality of G will be n choose 2, which is roughly n squared. And so the log of n squared is just log n. So finally you get a m dot log n size vertex curve. Okay. The size of the vertex cover is at most this much, m times O of log n. Okay. So we know that the optimal is m, and we got a m dot log n size vertex cover, and therefore this is a log n approximation algorithm. Okay, any questions on this? The computation we are doing, approximation factor. So GM as we defined here, so M is the total number of vertices in optimal vertex cover. Okay. So let's say the total number of vertices in the optimal vertex cover. So this is the smallest size vertex cover that is going to be M. And GM is just, so initially we started with this original graph. Okay. So I set G naught to be equal to G. And then I pick the maximum degree vertex in G naught and delete all the incident edges and get this graph G1. Similarly, I take the maximum degree vertex in G1, delete all the incident edges and get this new graph G2. And so on you do for m many steps. And the final graph, what you will get is called GM. Okay. Okay, any other questions? Okay, so if there are none, so that brings us to the end of this course. And yeah, I really enjoyed teaching you all. I think there were a lot of interesting ideas. Many of you will seem like they're genuinely interested in this course. Yeah, and I really enjoyed teaching you all. Uh, yeah, so any other questions if you have, you can ask. If something you have not understood in this course, I can go over that. But yeah, this is the end of this course. Okay. Syllabus for the NSEM is most everything. Just the last two lectures, they might not come. Okay. Because these were just to give you some additional practice in approximation factor, how to compute the approximation factor. Yeah, because this was just another example I gave you for a problem which you have already seen. But otherwise, everything is there in the instance levels. Okay. So it's the same pattern. Okay, 1 hour exam. Yeah.
Sir,
Yeah.
sir, it will be all MCQ or we have to write algorithm.
No, I don't think you'll have to write algorithm. So we are yet to set the paper. So I'll tell you the exact format in a few days. Okay.
Yes, sir.
Okay. Yeah, don't worry. If you are following the class, it shouldn't be too difficult for you. Okay. Yeah. So all of you are coming to the campus next semester, or what is it? Yeah, if you are coming, hope to see you here.
Sir, can you just
Yeah.
reiterate the pricing technique used in weighted vertex cover?
Yeah, yeah, sure. Let me, I will have to search for that thing. Yeah, tell me.
Sir, I'm not understanding the process we are doing here. We are just
Okay. So what was it? Yeah, so let's say we have this graph. These are the weights to the vertices, and what we want is the minimum weight vertex cover. Okay. So initially, we assigned some prices to the edges. Okay. And so let's say we assign the minimum possible, which is assuming that there are only non-negative weights. So we set the price to 0 for every edge. Okay. So that's what we did here, 0 to every edge. Okay. And then you try to increase the weights of these, the prices of these edges as much as possible. So we are trying to maintain this particular invariant, uh, that the sum of the prices of the edges should be at most the weight of, uh, sorry, no, yeah, this particular thing, that the sum of the prices of the edges incident with a particular vertex is less than equal to the weight of that vertex. Okay. So in this example, initially we set all of them to 0. Then we try to increase the weight of one of these. So we look at the minimum weight of the vertices incident with these edges. So in this case, it is 3. Okay. So we increase this weight to 3. Okay. And once you have increased the weight of these edges, you have to remove from that vertex that much weight. Okay. So this will become 4 minus 3, that will be 1, and this will become 3 minus 3, it will be 0. Okay. Then we picked another edge. Let's say we picked 1 and 3. Okay. So what is the minimum of 1 and 3? It's 1. Right. So we assign this price to be 1, and then again this will become 0, this will become 2. Right. And then we look at the minimum of 2 and 5. Right. It is 2. So we assign this price to be 2. This will become 0. This will become 3. Okay. So now all of these are 0 and 3. So you can't increase the price of any edge, right? Because all the edges are incident with at least 0 weight vertex, and that is when we will conclude, right? And whatever 0 weight vertex are there, those will be included in our minimum weight vertex curve.
okay, sir.
Okay.
Yes, got it.
Yeah. Any other question? Okay, then. So all the best for your end semester exam. So is there a question? No. Okay. So all the best for your end sem exam. It will be not too difficult. If you have followed the classes, all the classes, you should be able to solve it easily. Yeah. If you have any other questions, you can always email me. Yeah. Any questions or doubts? Okay. Thanks, everyone. Stop the meeting.
Thank you.
Thank you.
Thank you, sir.
Thank you.